Hello and welcome to the Tech Zero Python learning course. In this video we're going to be covering something a little more interesting. We're going to be talking about recursion. Recursion is the concept where a function calls itself. Python supports function recursion and it can be pretty useful. If we set it up properly, we can use it to loop through data or data structures like a binary tree, or we can use it to implement divide and conquer algorithms to efficiently reach some sort of desired result. For a recursion, you need at least two parts. You need a recursive step where the function calls itself, and what's called the base case, where some recursive branch will end up stopping, otherwise you get a infinite recursion, and that's a bad time. Python actually has a default recursion limit of 1000, and it'll stop you at that point, but we're not going to go quite that far today. An easy example of recursion is the Fibonacci sequence. If you're not familiar with the Fibonacci sequence, let's write it up here. Fibonacci, 1 and 2 seeds, is equal to, n is equal to n minus 1 plus n minus 2. And let's put some parentheses around that to make it a little extra clear. So we have Fibonacci of 0 is 0. We have Fibonacci of 1 is 1. Fibonacci of 2 is 1. Fibonacci of 3 is 2. Fibonacci of 3 is 3. And then so on, 5, 8, etc., etc. And you see how each number is the sum of the two preceding numbers. Now, how would we write a function that calculates that? We'll say def Fibonacci n. If n is equal to 0, return 0. It's just to cover the case where we pass 0 to it outright. If n is equal to 1 or n is equal to 2, return 1. Else, we return the function for n minus 1 plus the function for n minus 2. And that's that. That's it. It is as simple as that looks. So we come down here and we say print Fibonacci of, let's say, 10. And we get 55. 55 is the Fibonacci number for n equals 10. Let's say we do 30. That's a little slower. Did you notice that? Let's say 33. Ooh, that's getting a bit slow. 34? 35? Ooh. That is definitely getting slower, and there's a good reason for that. And it's something you should be careful of when writing a recursive function. If you have a recursive function like this, where it branches in places like this, you're going to end up with a pretty hefty time complexity. The Fibonacci time complexity for this implementation is big O of 2 to the n. What does that mean? That means that the upper bound for how long this is going to take increases by a factor of 2 for every single increase of the value of n. Meaning that if I go from 35 to 36, it's going to take twice as long for 36 as it did for 35. And that's going to continue all the way up until we're sitting here waiting for minutes for this thing to finish. And the reason for that is every time we branch, we have to calculate all of the Fibonacci values in this branch and then do it again in this branch. I actually made some graphs to demonstrate how this looks. And you'll see in this first one, we have n, and it branches to n minus 1, n minus 2. You'll see that n minus 3 appears in both branches. If we were to go a little farther on the leftmost n minus 3, that will have n minus 4 and n minus 5. And then we'll have the same thing on the right side. Now let's look at if we were going to go 1 up from n, and we go to Fibonacci of n plus 1, we'll see just how much more needs to be calculated each time we increase our n by 1. The entire subtree for n minus 1 from the first graph is going to be completely recalculated on the right end of the new branch. Put simply, for each increase in n, the number of calculations doubles, and thus the time to calculate each successive Fibonacci number just about doubles. So what if we want Fibonacci of n equal to 100 or 200? Well, we'd be sitting here for a good couple minutes waiting for that to come out. Is there a way to do this quicker? There is. With a concept called memoization. I'm going to write that out because it's memoization. Basically, what we do is we store the values of a Fibonacci number when we calculate them. So instead of recalculating them all the way back down these trees, we just reference something that is storing our values, and if it exists in it, then we're good. We just pull it out and use it as opposed to having to recalculate the whole thing. So how can we do that? Let's make another function to demonstrate. Let's say def Fibonacci m. And we're going to create a dictionary of Fibonacci numbers. We're going to call it fibstore. And we're going to populate it with our base cases. We're going to say for Fibonacci 0, we have 0. For Fibonacci 1, we have 1. For Fibonacci 2, we have 1. And we'll leave it at that. Now, in our Fibonacci m, we're going to have an inner function. We're going to call it def fib inner. And in here, we're going to say if n is in fibstore, return fibstore n. And that's that. If we already have calculated that value, we're just going to return it. Else, say fibstore n is equal to fib inner n minus 1 plus fib inner n minus 2. And that will create a new entry in the dictionary for fib inner n minus 1 and fib inner n minus 2. Now you might say, aren't you recalculating all these Fibonacci numbers when you do this? Well, no, because at some point you're going to hit the Fibonacci numbers that we've already calculated, and these are going to go much shorter. And eventually you're going to hit the point where we have so many calculated that it's just going to cascade and go just about instantaneously. And then from there we return what we just made, fibstore of n. Then we're going to come down here and we're going to make our return value for the outer function, return fib inner n. That way, remember this is just the definition of the function. We need to actually call it when we're in our outer function here. So let's test it out. Remember, it took a good couple seconds for Fibonacci of 36 to come out. What if we do it with memoization? That was pretty quick. Okay, well, let's say 37. Is that double like it did before? Nope. Let's say 200. Let's time 200. Okay. How about 2000? As you can see, it's much, much quicker. The time complexity of the Fibonacci sequence using memoization is not big O of 2 to the n, but simply big O of n. You'll need to calculate each value once, and then from there it's basically just constant time pulling it out of our fib store.